We continue with linear transformations by considering matrix representation of linear transformations. Okay, so straight up, we already talked about linear transformation, starting from the two videos from here before now, and we just need to remind ourselves briefly what that is about again before we move on with what we have to talk about. Okay, so linear transformations, of course, as you know, a linear transformation is a function T which maps an n-dimensional real number set to an m-dimensional real number set that satisfies the following properties for all vectors u and v and scalar c. So two things, there's additivity, such that the transformation of u plus v is the same thing as the transformation of u plus the transformation of v. Then there's homogeneity, meaning that the transformation of a scalar multiplied by a vector u is the same thing as the scalar multiplied by the transformation of the vector u. So every linear transformation can be represented by a matrix, and applying this, the transformation is equivalent to matrix multiplication. So every linear transformation can be represented by a matrix. And when we apply the transformation, it is equivalent to matrix multiplication. We've done something like this previously, but now we want to look at it in the proper way, in the name it is actually called. So let T map Rn to Rm be a linear transformation. So the standard matrix of T, so there's something called the standard matrix, and that's what we're looking at here in this second section. Standard matrix of a linear transformation. So the standard matrix of the transformation is the M by N matrix. So the M comes first, the M by N matrix A, such that you have the transformation of E1, transformation of E2, all the way to the transformation of En, where E1 up to En are the standard basis vectors in Rn. So these are the standard basis vectors in Rn. So for all vectors x in Rn, we have that the transformation of x is always equal to Ax. And of course, A is a matrix of certain values, as you're going to see in a jiffy. So let's talk about standard basis vectors. Generally speaking, in two dimensions, there are two standard basis vectors. You have E1, that's 1, 0, E2, 0, 1. In three dimensions, you have E1, that's 1, 0, 0, E2, 0, 1, 0, E3, 0, 0, 1. So it's more like you having the columns of unit matrices in these dimensions, basically. Okay, so now we go for an example which says to find the standard matrix. So finding the standard matrix, so let's T map two dimensions to two dimensions of real numbers, and let's be defined by the transformation T of x comma y, which is equal to 2x plus y comma x minus y. So this first step you want to take here is to apply T to the basis vectors. So if you apply T to the basis vector, so it means T of E1, T of E1 is T of 1, 0. All right. So if you have T of 1, 0, that means you're going to substitute x 1 for x and 0 for y. So that means 2 times 1 plus 0. That's 2 plus 0, which is 2. Then x minus y is 1 minus 0, which is 1. So since you're working in two dimensions, right? T of E1, you have 1, 0 for the first column, which is 2, 1. And for the second column where you have 0, 1, just like these two now, E1, E2. Then again, you substitute 0 for x here, that will go to 0, and you have 1 here. That's why this first one is 1. And then for the other one, x is 0, y is 1. So that's why 0 minus 1, you have minus 1 here. So the transformation, so don't forget the definition we have, that the standard matrix of T is the m by n matrix, such that take the transformation of the basis vectors up to the n degree, and that will be the standard matrix. So as we've got these columns now, right? So we got T of E1 to be 2, 1. T of E2 is 1 minus 1. So this step 2 now, you form the standard matrix. So these values you got here are now going to be the columns in the standard matrix, basically. So you have 2, 1, 1 minus 1. Thus, now you can say T of x is equal to AX in this case. So this is where this is your A actually, right? Now, we go on to talk about action basis, action on basis vectors. So action on basis vectors. So any vector x in Rn can be written as x equals x1 e1 plus x2 e2 plus all that up the way to all the way to x and en. So by linearity, now we say that T of x is equal to x1 T of E1, x2 T of E2, and all of that all the way to xn T of En. So this expression is exactly what matrix multiplication computes, as we see in the next example where we have this. So to apply a transformation, right, you have A to be 2, 1, 1 minus 1, the one we formed here, right, as a standard matrix, but of course totally has nothing in connection with that, absolutely. So it could just be any random matrix. So let A be 2, 1, 1 minus 1. Find T of 3, 2. So T of 3, 2 now, as we know, T of 3, 2 is meant to be AX, right? So T, as we see here, T of X is AX. Now we have our A to be 2, 1, 1 minus 1. So now 3, 2, 3 comma 2 now is like our X. So we have AX, and that'll be, of course, the usual multiplication thing we do. Let me open the worksheet for this now. Okay, so we have T, rather we have A to be 2, 1, 1 minus 1, I believe. I think that's what it is. Let me be sure. 2, 1, yeah, 1 minus 1, and then X now is 3, 2. Okay. Um, how did we get here again? What happened? What happened? What happened? Okay, yeah, this. Yeah, so 2, 1, 1 minus 1. That is the matrix we have. And then we need to find T of 3, 2. Okay, so we can just say X is 3, 2, like this. So now we need to find T of 3, comma 2. Okay, that's all we need to look for. So again, from what we learned already about matrix representation, we know that the transformation of X is the same thing as AX, right? So in this case, now that simply means we have T of X to be equal to A. This is 2, 1, 1 minus 1 multiplied by 3, 2, which we have there. So that means, of course, to multiply, I always explain that uh, you go and look at the number of rows in the first matrix. So look for the number of rows in the first matrix. So in the first matrix, we have 2 rows. So that means we're going to write this column twice. So T of X now is equal to 3, 2, 3, 2. 3, 2. Okay. Then afterwards, you put this first row 2, 1, put it over the top, 2, 1. Then the one down, 1 minus 1, put it over this. So you can then have T of X to be equal to 3 times 2, 6, 2 times 1, 2, 3 times 1, 3, 2 times minus 1, minus 2. So at the end of the day, Tx is equal to 8, 1, like that. So, and that's how you get. Oh, so did I say Tx? I should have said 3, 2. T of, okay, well, it's T of X, right? Or you can say 3 of T of 3, comma 2, 3, comma 2, 3, comma 2. But if you see T of X, it's fine because I already said X is 3, 2 up there. So T of 3, 3, comma 2, T of T 3, comma 2. So that ends up being 8, comma 1, like this. So, and that's exactly what you have here because A is multiplying 3, 2. Now, what is the geometric interpretation of this now? So each column of the matrix shows where a basis vector is mapped. So each column like this shows where this basis is matched. So you have 2, 1 multiplying this. So 2 times 3, then 1 times 2, like this. Then 1 times 3 down here, then minus 1 times 2, like that. So each column of the matrix shows where a basis vector is mapped. Then the transformation of all vectors follows from the transformation of the basis. Then the grid of Rn is stretched, rotated, or shared accordingly. So, in the last video, we talked about the geometry of linear transformations. Okay, so the grid of Rn is stretched, rotated, or shared accordingly. So if you want to refer to that video, I actually demonstrated using Desmos how a rectangle can rotate, how it can be scaled, how it can be shared, and how it can be reflected. In fact, I feel like flashing that right now. Maybe I should just do that. I have the pictures on my desktop. Okay, let me just go to the desktop first. In fact, I made my front desk with that, my background with that. Okay, see what I'm talking about now. So this is for scaling now. So this is, imagine the original matrix, the original triangle. If once you see prime, it's not the real thing, the original. So this is the original one. So we can scale it, we can double it, and we can halve it. We can double it and halve it. So the shape, the shape is maintained, but then the size is reduced. Then next, now we have this is about rotation here. This is about reflection rather. So this is the original thing. So you can reflect it about the x-axis, about the y-axis, and then you can reflect it about the x-axis. That's for reflection. Then we also have shear. Shear is like some kind of stretching. Stretching. You can have vertical shear and horizontal shear. So the area is retained, but then the angles are twisted because you're stretching out the shape. And then you also, of course, have rotation. So you can rotate. This is rotation by 90 degrees clockwise, no, anti-clockwise. This is 90 degrees clockwise, and this is 180 degrees. Now, if you rotate it by 270 degrees, you come back to the same thing as 90 degrees anti-clockwise, I believe. So those are the things we considered when we talked about the geometry. So here now it's telling us that the grid of Rn is stretched, rotated, or shared accordingly. Now let's move on to talk about composition of linear transformations. So if we let a transformation mapping Rn to Rm, and if we let T be a transformation mapping Rn to Rn, and S is a transformation mapping Rm to Rp, then the composition of S and T is defined by S of T of X, which is S of T of X like this. And then we can then have the matrix representation. If A is the matrix of T, so if A is the matrix of T and B is the matrix of S, then S of T of X will now be B of A of X. That is B of A X, like B times A X, like that. And then we see here that matrix multiplication is not commutative. So in general, B of A is not equal to A of B. I've shown that in the previous video that matrix multiplication is not commutative, except if A and B are equal. That's the only condition for matrix, for two matrices that multiply to give the same result. So look at this here now. So we talk about composition. So composition is basically matrix multiplication. That's the essence of everything we've been talking about. So if A is 1, 2, 0, 1 and B is 2, 0, 0, 3, find the matrix of S of T. So the matrix of F of T is as good as, because we already know that A is the matrix of T and B is the matrix of S, like what we had up there. So if A is the matrix of T and B is the matrix of S, right? So if you need S of T, that means we have BA. So that's matrix B multiplied by matrix A. And of course, that's so when we multiply that, we get 2, 4. So it's like 2 times 1, 2 plus. So you take this column, right? 2 times 1, 2 plus 0 times 0. That's 2 plus 0, 2. Then again, we have 2, 0 multiplied by this column, 2, 1. So 2 times 2 is 4. 0 times 1 is 1. So yeah, that's why you have 4 here. Then again, you have 0, 3 multiplied by this column. So 0 times 1, 0. 3 times 0, 0. So that's why we have 0 here. Then again, you have 0, 3, and 2, 1. So 0 times 2 is 0. 3 times 1 is 3. So in case you don't understand that, let me do it on the worksheet again. 1, 2, 0, 1, 2, 0, 0, 3. Okay. 1, 2, A is 1, 2, 0, 1, and B is 2003. So in this case now, we need S composed with T, and that is equal to BA. And that means we have 1201 multiplied by 2003. And like I've always explained, an easy way to do this is to just say BA now is equal to. So go look at the first matrix. How many rows does it have? It has 2 rows. So that means you're going to write each column twice each. Okay, so that means you have 2020 and then 0303. So having done that, then you can come back here and say on top of 20 now, you can put 1 2 each. So the one at the top, 1 2 1 2. Then next you have 0 1 down, you put it over the 0 1 0 1. So in that case now, you see that BA is equal to 2 times 1 2, 0 times 2 0. Then 0 times 1, 0, 3 times 2, 6, 2 times 0, 0, 0 times 0, 0 times 1, 0, 0 times 0, 0, 3 times 1, 3. So finally, BA is equal to 2603. And that's done. Okay, easy peasy, like they say. Then we move on to the summary, right? Okay, this is a fast one. So, because it's all about matrix representation of linear transformations, right? So, every linear transformation can be represented by a matrix. That's what we have discovered. The columns of the matrix are the images of the basis vectors. Okay, then applying a transformation equals matrix multiplication. Then composing, so when you do matrix multiplication, it is technically applying a transformation. Then composing transformations corresponds to multiplying matrices. Then the order of multiplication, of course, matters. So let's see some practice problems. Let me see if I may do one or two of them, if necessary. And if not, I'll just move on. So let me show them in fives. Let's show them in fives. Can we show you in fives? That'll be too small, but so I can show as much as it can take. So 4 can show very well. So let R squared be mapped to R squared B, T of xy, which is 3x minus y, 2x plus y. Find the standard matrix of T, okay? And use the matrix to compute T of 1, 2. Okay, I think I want to do this, all right? So T of xy equals 3x minus y, 2x plus y, okay? So I'll practice now. So T of xy is equal to 3xy, 3x plus y, right? 3x plus y, then 2x minus y. Let me be sure about that. 3x, okay, 3x minus y, 2x plus y. 3x minus y, 2x plus y. Okay, 3x minus y, 2x plus y. So we have to find the standard matrix of T. Okay, so A, standard matrix of T. We need to look for that. That's the first part. Then B, we need to look for, use the matrix to compute T half. So compute T1 comma 2. Did I say T half? That's T1 comma 2, yeah. T1 comma 2, not T half. T of 1 comma 2. Okay, so that's the question we have, the very first question. And you can see this is two-dimensional, right? That's R squared to R squared, like this. So in this case now, what's the first thing we do? Uh, First of all, you are going to say, look at this now. We want to find, so A, the standard, to find the standard matrix, find the standard matrix. Okay, we know the standard matrix A is equal to T of the, since we are talking in two dimensions, so the standard matrix is the matrix of TE1, that's the standard, the basis, and then TE2. Okay, maybe no comma is needed. TE2, I mean TE1, TE2. So a matrix that contains this is what we are looking for at the end of the day. And since we are talking in two dimensions, we know that E1 is 0, 1, and E2 is 0, is 1, 0. 0, 1, no, E1, sorry, is 1, 0. E2 is 0, 1. So now that that is taken care of, the next thing we then want to do is to, since we know that given given that T of x comma y is equal to 3x minus y, that's 3x minus y and 2x plus y, right? So then we know that T of E1, which will form the matrix at the end of the day, T of E1 is equal to, T of E1 is T of 1 comma 0, which now means that we have 3, 1 minus 0, comma 2, 1 plus 0, like this, so that T of E1 now is equal to 3 minus 0, that's 3, and this is 2. So we have 3, 2, which is necessary for the matrix later. Then we have T of E2, which is T 0, comma 1, which is now going to be 3 into 0 minus 1, comma 2 into 0, 2 into 0 plus 1. That's 2x plus y. That's using these two now, like we did. So now we have T of E2 equals 3 times 0 is 0. That's minus 1. 2 times 0 is 0 plus 1. That is 1. Okay. So now, having done all that, then we say that so the standard matrix, the standard matrix A, which is equal to um T E1, T E2, is going to be the same thing as TE1 already is 3, 2. So we have 3, 2 here, and the other one we have minus 1, comma 1. Okay, so this is the standard matrix we are looking for. So the next part is we need to compute T half. All right, I mean T1, comma 2. I wonder why I'm calling that T half. So T1, comma 2. Okay, okay. B now to compute T1, comma 2. We know already that T of x is always given as AX, where A is the standard matrix we just computed. So in this case now, here we can say that A is what we just computed, 3, 2 minus 1, 1. Yeah, 3, 2 minus 1, 1. Yes. And then we have X to be 1, 2. Okay, X is 1, 2 as given here. So then we can say that T1, comma 2 is equal to A, which is 3, 2 minus 1, 1 multiplied by 1, 2. So that, like I said, check how many rows do we have here? 2. So it means you write this column twice. So we have 1, 2, 1, 2. Then you put 3 minus 1 at the top, 3 minus 1. If you add more rows, you put it at the top across. Then this is 2, 1. Put it at the bottom. So we have this. So this is T, comma 1, 2 now. So that you now have T, comma 1, 2 to be equal to 1 times 3 is 3 plus 2 times minus 1, that's minus 2. All right. 1 times 2 is 2. 2 times 1 is 2. So finally, we have T of 1, comma 2 to be equal to 3 minus 2, that's 1. 2 plus 2 is 4. And then that is what we have. So T1, 2 is 1, 4, like for this now. Okay, so this one, now let T be R3 to R2, be a linear transformation such that we have T of E1 to be 1, 0, T of E2 is 0, 0. Okay, so these ones are specified now. T of E3 is 1, 1. Find the standard matrix of T and compute T is 2 minus 1, 3. Okay, so we want to find the standard matrix of this now. Well, we have not been given the, so you want to find this. Okay, TE1 has been given already, so you need to find the standard matrix of T. So in that case, now it's going to be 1, 0, 0, 0, 1, 0, and 1, 1, 0. Because, okay, this is, okay, 3 by 3 becoming R2 now. So, yeah, and you have this. So since we already have this one, you just put them up in the matrix, and then you have, and then you can then compute 2 minus 1, 3 by multiplying them out like that. Okay, so number 3 says let A be 1 minus 3, 3, 0. T of x is ax. Compute T of 4 minus 1. So you just multiply this by 4 minus 1, the column matrix. Then let T be R squared by R squared, be linear transformation that rotates vectors counterclockwise by 90 degrees. Find the images of E1 and E2. Okay, then write the standard matrix of T like that. Then we have 5. Let's look at 5 to 7. Let R squared to R squared be a reflection across the x-axis. Find the standard matrix of T. Okay. Then compute T of 3 minus 5. Then, I mean, try your hands on all this and let's see how it goes. So let A be this, let B be that. So S of T is going to be BA and T of S is going to be AB. Compare the results, most likely they are not going to be the same because matrix multiplication is not commutative. And then let R3 be mapped to R3 be defined by this. So T of XYZ is this. So find the standard matrix of T. Of course, you already know what to do here. So the standard matrix, you need T of E1, E2, E3 because you're working in 3 dimensions. So E1 is 0 1 0 0, E2 is 0 1 0, E3 0 0 1. So you are going to fix all of that up here, and then you are going to get you get TE1, TE2, TE3, and put them up in a matrix. Then multiply that matrix by 1, 2, 3 in computing T of 1, 2, 3 like that. So suppose T maps R squared to R squared has standard matrix. This describe geometrically what t does, then find t to which is 2 comma 0. Then let t be r squared to this be a linear transformation such that t11 is 2 3 and t11 minus 1 is 0 1. The standard matrix, of course, is already okay. You now need to find the standard matrix of t, right? So you do all of that. Okay, so yeah, with this, we come to the end of this interesting video with matrix representation of linear transformation. Try your hands on the practice questions as much as you can. If you need help with any, let me know. I may make separate videos to solve whatever problems you may have issues with. All right. So having done that, of course, let me know. I mean, if you have subscribed already, I must thank you very much. If you haven't subscribed, you'll be missing a lot because there's a whole lot to learn on this channel. So why not go ahead and subscribe right now, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join, and that gives you some special privileges like getting some videos only for members, of members seeing some videos first before others see them, like hanging out or requesting for my PDF copies of my notes that I use for some of these topics. And then of course we can hang out together. I can consult for you depending on your level of membership. Ultimately, let's don't forget to comment, like, and share so that more people have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.